dissociation energy is to break in the middle. Okay, so that generates radical. That's what we call homolytic. Homo means the same, hetero means different. So it generates radical heterolytic cleavage may generate the ion, one positive, one negative, and this energy about 100 kilocalorie per mole. That energy is matching to UV light. If it's breaking in UV light, then 우린 끌어다니다 다 깨지겠지. 그래서 좀 더 강한 에너지가 있어야 반대 디소시에이션이 일어날 수 있어. 그 얘기는 밖에다 햇빛 잘못 쬐면 반대가 막 깨진다. 문제가 있네. Okay, ethane has a CH3, CH3. They rotate, right? And then those rotating generate the different conformational isomer. There is a stable form, eclipsed form, kind of things. If the connectivity is changed, that's what we call structural isomer or constitutional isomer. Constitution is a structure. Constitution is humble, is a basic structure of the constitution. So connectivity changes structure, constitution is the same, and conformational isomer is specifically applied to ethane, but at the same time there's a kind of a stereoisomer too. So answer is 1 and 2, also the answer. Okay. Conformer is a conformational isomer. Conformer is generated by rotation, right? Vibration is too short, so it's just vibrating like this, and we cannot distinguish those vibrating the isomer. So this is determined by rotation, and that energy which goes over this eclipsed form, that's what you call this string. If it goes like this, there's two kinds of strain, right? One is a static strain, the other was torsional strain. Torsional means it's by rotating, going over like this. This is torsional. Okay, so two strains we learned: static strain and torsional strain. And conformer or conformational isomer is formed by rotation, and it's not resonance. Why is it not resonance? If it's not resonance, it should be equilibrium, right? What is the big difference between resonance and equilibrium?
레저넌스는 아토믹 스트럭처를 제외하고 전자 배치만 가는 거지만 이퀄리브리엄은 이제 아토믹 스트럭처까지 전부 다 다른 형태예요.
자, 키워드만 뽑아서 얘기하면 일렉트론만 움직이는 게 레저넌스다, 그지? 로테이팅 하니까 아톰도 움직인 거지. 그래서 그거는 이퀄리브리엄이야. 컨포메이셔널 아이소머는 이퀄리브리엄이야. 레저넌스가 아니고. Okay? And tautomer is the isomer of proton is moved, right? So in that case, the connectivity is also changed, not only conformation. Tautomer is a more serious isomer. Conformational isomer is in equilibrium at room temperature. Okay? At least the atom has been moved. That's why this is not resonance. This is equilibrium. Okay, 1H to 1H, that is about 4 kilojoule per mole, right? And if it's eclipsed form, it has 3. So I asked not single pair in ethane between staggered form is a little more stable. 3 of the 4. That's why the total difference is 12 kilojoule per mole. Okay, one overlap was about 4 kilojoule per mole more stable. Okay, energy-wise, the staggered form has also 2 forms, right? Anti and gauche is both of them are staggered form. But methyl group-wise, this is anti form, this is gauche form, right? Gauche was a little less stable than anti form, so anti is most stable. The next one is gauche, and then eclipsed-wise, this one methyl hydrogen, the proton hydrogen is next, and most unstable one is methyl-methyl. That's a pushing further, right? It has torsional and also static units together, static strain together. Okay, so it has 4 different conformation there, right, in butane. Okay, this is the most stable, this is the most unstable, bottom to top. In ethane, there was a 12 kilojoule per mole. In butane case, methyl versus anti, it's about 19 kilojoule per mole. Okay, in the textbook it said 3.8. That specific number is not so important. Approximately 4 kilojoule per mole. 뭐 자꾸 숫자를 자꾸 물어보시나요? 한 번쯤 이래야 머릿속에 좀 들어가겠지. Proton, hydrogen, hydrogen, about 4 kilojoule per mole. Okay, 3 of them 12. Butane, methyl becomes 19. And gauche versus anti is also about 4 kilojoule per mole. Approximately 1 kilocalorie per mole. 1 kilocalorie is 4.2 joule, right? So this is the range of the energy we are talking about. 4 kilojoule per mole is approximately the range we are talking about rotational energy. Okay. Okay, isopropyl is 1, 2 ethyl, 1 methyl, 2 ethyl, isn't it? This is a connecting point. Why 2 methyl? 2 methyl ethyl is 2 methyl ethyl is this, correct? It's not isopropyl. This is just propyl, correct? This is a 2 methyl ethyl, right? How about the third one? 1 ethyl methyl, 1 ethyl methyl, that's also propyl, right? How about the first? 2 ethyl methyl, it's impossible because methyl is only 1, right? So this doesn't exist. This one and this one has a wrong naming, right? 안 헷갈리지? 계속 물어볼 거야 지금. 잘 정리해. This is a connection point. 1, 2, 3, and 1 methyl to ethyl. This is 1 methyl to ethyl. Okay, now we move to butyl. Okay, this is a sec butyl, and this is 자꾸 틀리지. 1 methyl propyl. This is a sec butyl, isn't it? How about the second one? 2 methyl propyl. This is a 2 methyl propyl. Okay, this is different. Third one, 3 methyl propyl. 3 methyl propyl is a normal butyl. Right? Last one, 2 ethyl ethyl. 2 ethyl ethyl. That's also simple butyl. Correct? So sec butyl is 1 methyl propyl. This is sec butyl. Okay? Okay, good. So this is one position, 1,1 dimethyl ethyl. That is the T butyl. Okay. Okay, move on. One, two dimethyl ethyl. This is isobutyl. Okay. This was a sec butyl. This was a sec butyl. Tertiary butyl. This is a tertiary butyl. Okay. 여기까지만. 그 다음은 안 할게. 펜틸은 안 할 테니까 부틸까지는 알아두자. Isopropyl, isobutyl, sec butyl, T butyl. Okay. Up to here. 여기까지는 알아두자. 밥 먹듯이 할 수 있게. Okay. Last problem. 1분 시간 준다. Okay, let's check one by one. First one. Methyl, ethyl, what's wrong? 2 methyl, 3 ethyl, what is wrong? Alphabetically, ethyl should come first. Numbering, we need to give lowest number, but once number is given, then the order is alphabetical order. Ethyl should come first. Then this should be 3 ethyl, 2 methyl, if the structure is correct. Okay. Second one, dimethyl, ethyl, then alphabetically here also, D comes first, then E. No, we don't count this die, right? So we count M and ethyl as alphabetical order. Again, ethyl should come first. 3 ethyl, 2 dimethyl, right? But as we learned from your TA, and here, if that is in the parentheses, then this die is also counted as alphabet. That's why if you compare this die and this ethyl, then die comes first. Okay? So if it is simple separate one, then we don't count this die. Alphabetical order-wise, ethyl methyl is compared. But if this goes into parentheses as a separate group, then any alphabet comes first. That is counted as alphabetical order. Okay? Last one, what's wrong here? Sec, and you need to put dash, right? Sec, dash. Third, dash. Iso, no dash. Iso, no dash. Okay? So this is the review of the nomenclature of alkane. Oh, 지금 축하해. 오케이. 지금 통좀 받은 적 있어?
네.
아 그래? 그럼 넘어갈게. Okay, today we study about cyclic alkane. We already practiced with the cyclic alkane. Cyclic alkane is -2 hydrogen, right? To connect the end, then we need to remove 2 hydrogen and it was connected. Right? So cyclic alkane, if it's a single cyclic form, the general formula should be CnH2n. Right? General alkane was 2n plus 2. Right? So here CnH2n. So we have the various structures which is a cyclic form. Even triangle structure is also possible. Then triangle 3 carbon propane. So cyclopropane, cyclic propane, and then sometimes we see this kind of 5-membered ring, and even it can be fused ring. One ring is sharing one edge, and this is what we call fused. Okay, not only connected, and fused ring, this is the basic structure of a steroid. So this kind of a structure is very commonly found in nature. That's why we study about the cyclic alkane. Now, naming. Now, if it has this kind of ring, 3 cyclopropane, 4 cyclobutane, 5 cyclopentane, 6 cyclohexane. And for the abbreviation, for ethyl group, we say ethyl. Methyl group, methyl. Propyl group, propyl. Butyl. Above that, usually we don't use much of that abbreviation. Okay, at least this much you need to catch. Methyl, ethyl, propyl, butyl. Okay. Now based on this, cyclohexane up to 6-membered ring you have seen. Now if it's connected to other side chains. Now this one, core structure or mother structure is cyclopentane, and you can use this as methyl group here, methyl cyclopentane. Why don't you put here 1-methyl cyclopentane? If there is only one position, then 2, 3, so all has the same meaning, and you don't need to put. Then the simplest version we take. Okay, only one, then just methyl cyclopentane. Again, no space, just the whole word. Okay, how up to here, simple. Second one, this is propane, and this is 1, 2, 3, 4, butane. Then you have two options. One option is butyl cyclopentane, right? Or cyclopropyl butane. If it's butyl cyclopropane, then again you don't need to give number because it has only one position to add. But if you go the other way, cyclopropyl butane, then you have option of 1, 2 different options, right? That's why you need to give one cyclobutyl, one cyclopropyl butane. Then which one you should choose? Longer one. Here this is a 4 carbon, this is 3 carbon. Then you take longer one as the mother the structure. What if they are saying? In this case, this is the butyl cyclopropane. But if it's a 3, then propyl cyclopropane. Then what do you think? Which one goes higher priority? Cyclic means. Okay. So if it's the same carbon number, then you use cyclic form as the core structure. Then the name should be propyl cyclopropane. Okay, makes sense? Not go the other way. Okay, so longer one, or if it's the same, then cyclic structure take the priority. Okay, so based on this, cyclohexane and 2-methyl, and now we start to give the numbering. Then 2-methyl option is 1, 2, 3, or 1, 2. So here 1, 3, or you can go the other way. 1, 2, 3, 4, 5. So 1, 3 or 1, 5 is equivalent. Equivalent, then what should you choose? Smaller number. Okay. Basically, both of the name you can draw those structure, but if there's an option, then you choose lower number. Not 1, 5. You choose 1, 3. Easy, right? So dimethyl cyclohexane. Okay. And you need to give the number here 1, 3, 1,3 dash dimethyl cyclohexane. Capital or not is not important, but comma, dash, these are all important. And no space in between here. Okay, dimethyl cyclohexane and position. How many members are in here? 교수님 있으세요? How many members there? 7 members during, then heptane and cycloheptane, right? Cycloheptane, position-wise, now 3 of them. Now we have several options. 1, 2, 4, or 1, 3, 4, or if you go the other way, 1, 2, 3, 4, 5, 6, 7, 1, 5, 7, you have a different the system there, right? In that case, what you should choose? You choose lowest number. 1 to 4 is the lowest number. Okay, here 1 to 6, 1, 3, 4, these are all has a higher number than this. So you decide the numbering first. Lowest number. So it's similar to the branch of the alkane. When we handle the alkane naming, we started to use the first branch, right? Because that gives you lowest number. And then you decide second branch if the first branch is the same. In that case, you could start either from here or here to end. But here the problem is this is cyclic form. This is not permutation. This is combination problem. 순열이 아니고 cyclic 고리 순열이니까. cyclic form이니까 어느 쪽으로 갈지 양쪽이 다 가능하니까. So in this case, you need to choose. Try different numbering and choose the lowest number. 1, 2, 3, 1, 2, 4, 1, 3, 4, and 1, 2, 6. You can give a different numbering. You choose lowest number, and then you give each the substituents with alphabetical order. Okay. At the comes first, then methyl, then you give this one numbering first, and then 2 ethyl and 1 for dimethyl. Okay? Give lowest number first, and then alphabetical order. 이 표정은 뭐지? 연습이 필요하겠지. 연습 좀 해야 돼. Okay, how about this? Now we have option 5-membered ring, cyclopentane. It's a 1-2 position, right? So anyway, 1-2 or 2-1. Now your option is comparing ethyl versus methyl. So then, in this case, it's equivalent. 1-2, 2-1 is equivalent. Then you choose alphabetical order first. Then this alphabetical order take 1. Okay. Previously it was a 1-4, 1-3-4, so you chose 1-4. But in this case, either case, 1-2, 2-1 is the same, right? Then alphabetically, first one take the lowest number. Okay. 1-ethyl, 2-methyl, cyclopentane. 말로 들으면 다 당연한 얘기고 그럴듯한데 막상 하려고 하면 금방 안 되겠지. 숙제 미리 내놨어. 가서 숙제 미리 하면 돼. 그리고 기특하게 경민이가 수업 노트를 올려줬는데 정리를 꽤 잘했어. 그래서 각 챕터별로 수업 노트를 올려놓을 테니까 여러분도 수업 노트 잘 정리해가지고 친구들하고 나누고 싶으면 나한테 수업 노트를 보내줘. Okay, 4-membered ring, cyclobutane. Cyclobutane and 1-2 position. Then now by reading those names, bromo, methyl. Then bromo is B, so bromo comes first, and methyl. 1 bromo, 2 methyl, not 2 bromo, 1 methyl. Okay. Same situation, right? Same numbering, then you choose the alphabetical order. Okay, let's practice it here. Cyclohexane and 3 positions, 1, 3, 5 position, right? In any direction, it will give you 1, 3, 5 position. Then you need to choose lowest one first. Which one is the lowest? Bromo, methyl, ethyl, which is lowest? Bromo is alphabetical order-wise, it's first. And then methyl, ethyl, they compete again. Then ethyl, and then methyl. Makes sense, right? And how about this? Now 1, 2, 3, 4, 1, 2, 3, 4, same carbon number. Then you take this one as scheduled. Okay. So here now 1, 2, 3, 4. If you choose this one, cyclobutane, then this one. There's 2 options here. 1-methyl, 1-methyl propyl with the parentheses. That's one option. Or this one is sec-butyl. Both of them are acceptable naming. Sec, T, tert, and iso, those are accepted. Okay. But the core structure-wise, mother structure-wise, if it's the same carbon number, you choose cyclic form as mother structure, cyclobutane, and sec-butyl cyclobutane, or 1-methyl propyl cyclobutane. No space. Okay, last one. Here, cyclopentane. Now 1, 2, 3. Right? 1, 2, 3 position. Then your competition is 1 and 3. Because it goes this way and this way, and it has only 2 options, right? In this case, 1, 3, 5, you have 2 options, go this way or this way. But in this case, you compare this one and this one. Ethyl versus chloro. Which comes first? Chloro comes first. Right? C. So 1 chloro and 2 ethyl, 3 ethyl and 2 methyl. So you give a number first, and then alphabetical order. 부작이 어렵진 않지. 대충 따라가긴 하다, 그지? Okay, so this is naming, but definitely you need to practice. 연습 많이 해. Okay, now let's just think about the conformational change. When we studied alkane, there was rotation can happen through this single bond, and those generate conformational isomer, and it forms eclipsed form and is typically unstable and staggered form. So that's what we have seen, right? Those are conformer, not resonance, in equilibrium, and they are kind of easily convertible isomer. So that's why it is conformational isomer we call, but at room temperature, they are very fast moving to each other. That's why it's more like an equilibrium, not isolatable isomer. Okay? Now, comparing to this open form of alkane, cyclic form, the cyclopropane, they can rotate here. It's connected together. They can twist a little, but it's impossible to fully rotate unless they break the bond. Right? So that's why in cyclic alkane, there's no rotation. There's no real rotation. There's a small movement like trickling like this, but they cannot rotate. This rotation happens only when it is open form. Now, based on this, if you look at this structure, it's not rotatable. That's why in butane case, we had methyl group here and methyl group here. They are rotating, so it forms antiform, Cauchy form, staggered form, another staggered form. They can change to each other by equilibrium. They move very fast, but in cyclic form, they cannot fully rotate. So that's why this position of 2-methyl, they cannot be easily changeable to the other one, right? That's why this is real isomer, stable isomer, but connectivity-wise, when we said structural isomer or constitutional isomer, constitution, structure, we count their connectivity. Connecting this carbon to this carbon. From this carbon to this carbon, it's the same here, but this carbon, carbon to carbon, carbon to carbon. If you just say those are linkage but connectivity, it's the same. That's why we don't call this as a structural isomer. This is just in the position in the space is different, either this form or this form. That's why this kind of isomer has a special name as we call stereoisomer. Conformational isomer is kind of stereoisomer too, but they are very fast moving isomer we call special stereoisomer. That's a conformational isomer, but this is a stable stereoisomer. Okay, so in this case, then if you have these two structure, if you give a name, now so far we didn't count that stereoisomer case in open alkane. In this case, naming of this 1,2-dimethyl cyclopropane, right? But now we need to define whether this is in the same direction or opposite direction. Cis or trans, we need to give. So the rule is, if there is any chance to have two different possibilities, then we should designate which one is the case. If you don't need it, then we don't give. Right? 1-methyl versus a simple methyl. If there's no other option of 1, then we don't use 1. Same situation here. If you need to distinguish these two, then we give this. So cis-trans is giving you stereoisomer notations. Typically, this one I have seen before. If there is any double bond, then same direction, this is cis form. Opposite direction, this is a trans form. Similar situation. From this carbon to connectivity to this X, this one to this X, connectivity is the same, just the position is different. So this is another example of a stereoisomer. Okay. So isomer, structural isomer, has a different connectivity. And same connectivity and different position, this is stereoisomer. If they can be easily convertible by rotation among stereoisomer, we call this conformational isomer. Okay? Okay, so here's the example. Constitutional or structural isomer, it's the same meaning. Constitutional isomer is same butane, but this is connectivity is different. If you write this chemical structure by writing, you can say C1 is connected to C2, and if you write this one, connected to C3 and C4. Maybe this is one way you can write the structure, right? Chemical structure by the coding like this. But first one, you need to say C1 is connected to C2. If you shoot one line, maybe one way is you can do C3 and C4. Actually, there is some notation to write chemical structure like this way, SMILE code and different kind of connectivity based the text, the structuring, use that kind of a notation. So in this case, we can denote that connectivity is different. This is what we call structural isomer or constitutional isomer. Okay? But here, connectivity is basically, if you write this way, you cannot distinguish. It's the same structure you can draw for both of them. In this case, we need to give separate term, cis or trans. Okay? That's what we call stereoisomer. Stereo means three-dimensional, right? Three-dimensional position is different. Okay? Now, based on this, now we think to give a name of this. Previously, we didn't think about the position, but here, cyclobutane is a basic structure, right? And 2-methyl. And position-wise, 1,3 position, right? Then 1,3 dimethyl cyclobutane. And now we need to give the information about whether this 2-methyl is the same side or different side. Then same side, and then we put cis 1,3 dimethyl cyclobutane. Okay. If I give you the structure like this way, intentionally I did not give you the information about spatial positioning of these two, then you don't need to give cis or trans because you cannot give. This can be either mixture or maybe the information is not known. In the case, you just simply say 1,3 dimethyl cyclobutane, even though it has two possibilities. Sometimes we cannot get that information, or intentionally we use the mixture. Right? So in this case, if you want to draw that way, then one note is like this. It is coming out from the plane, coming out. If it goes in, you draw this way. This means from this point, this goes in, this comes out. If I draw the other one, okay, this is a cis, right? How about this? Trans, how about this? This is also cis. This one, if you turn over, this one and this one is equivalent. Right? Okay. Now, based on that, now we should look at this one. 1,3 position, cyclopentane, 1,3 position, and then naming wise, bromo versus ethyl, bromo wins. So bromo comes first. 1 bromo, 3 ethyl, cyclopentane. Structure wise, this one and this one is the opposite side, so we give name as a trans. Usually when we compare those cis and trans, usually we compare the same motif. Here, methyl. In this case, maybe the fair way is maybe proton, you may compare. Those are in the trans form. Then if it's all four are different, bromo, chloro, proton, ethyl, then we need to think which one we should take, those are comparison. That's what we're going to study next week. Okay, stereochemistry side. But simple way, cis and trans, usually you take same one or bigger same one. Okay, 2-methyl, and in this case it doesn't matter, methyl or proton. In this case, you compare this one to this one. Okay, based on this structure, we have a different kind of the natural product. Now, if you look at this, the final membrane, hydroxyl groups, you see 2 hydroxyl groups. What's the relationship? Cis or trans? It's a cis, right? Go in, correct? If you look at this hydroxyl, both of them are cis. For this ring, this alkyl group and this alkyl group, 2 alkyl group, if you compare, what's the relationship? That should be trans. This goes in, this comes out. Okay? So to define cis or trans, then you need to designate which one you are comparing. Okay? If it doesn't say anything, the common assumption is same motif, hydroxyl to hydroxyl, or proton to proton. Okay? But if it's designated 2 alkyl, what's the relationship? Then we should compare this one to this one. Make sense? Okay, now we move into the energetical of the problem. So last week we studied about the strains. We learned the 2 strains. Torsional strain, when it goes over and it has some strength, that's a torsional strain. It cleaves to the stable form. The other one was steric strain, even though its gauche is not torsional, but still it has some pressure in between. This gauche versus anti is far away, this is a little more stable. So we learned the 2 things, steric versus torsional, 2 different kinds of strain. Today we learn another one, ring strain. When they form ring, comparing to open form, ring structure generates extra stress. Extra stress, in chemical terms we call strain. Ring strain is a form, and this is energetic difference. Comparing to open form, interestingly, 3-membered ring. 3-membered ring has very high strain. 4-membered ring is also relatively quite high. 5 is quite reasonably low, but 6 is almost 0. 6-membered ring is quite stable, it means. Comparing to open form, it's almost the same. And then it is a little increased and then decreased. If it reaches up to 14-membered ring, quite a big ring, right? In that case, it's almost like open form. It's almost like a move freely. But up to here, we don't handle much. Our main interest is here. 3, 4, 5, 6. Okay. If you look at those structures, tetrahedral structure, tetrahedral 1, it has an angle of 109 degree. Right? Tetrahedral of carbon, 109 degree, and this is kind of most comfortable, the angle. Now if it is 3-membered ring, it's a 60 degree. Then the difference between 109 to 60 is almost a 50 degree. 50 to 60 degree means it's a very happy at this configuration. Now it's kind of shifted maybe the other way. This one is happy. It's I don't know. And then you can see those quite extra strain is applied to here. Right? 4-membered ring is a 90 degree. Looks like it's better than the 3-membered ring. Still, we have seen here 4-membered ring is also quite stressed, the strained form. 5-membered ring is much better. Now the difference is, in a sense, 108 degree is very close to 109. 5-membered ring maybe should be compared to 6-membered ring. 6-membered ring is a little bigger, 120 degree. And that is like a 11 degree difference. Then by looking at this structure, we may predict that which one may be most stable. Should be 5-membered ring, right? By looking at this angle. But in reality, that's a 6-membered ring because the structure is not planar. The carbon structures are 3-dimensional structure. That's what we are going to learn of that conformation of the ring structures. 3-member ring, cyclopropane. No other options. They are bound to each other. This 3 point can define one plane, correct? 2 point can define one line, correct? 3 point can define only one plane. There is no other option to move much. So that means cyclopropane is a perfectly eclipsed form. Right? No other options. Any direction you move, still it's the same plane. So that means if this is 109 of sp3 linkage, then in cyclopropane structure, this is 90 degree, 60 degree. So this overlapping is stronger and bigger than the bond is also stable. But this is pushed out like this. Originally 109 is pushed out, so it's partially overlapped. That means this bond dissociation energy can be smaller than regular CC bond. Bond dissociation is smaller means it's easier to break. Means the energy is higher. That means it's more unstable. Right? Stable means energetically it's a lower energy state and it's more difficult to break. That's why bond dissociation energy is bigger. If it has a strain like this, it becomes unstable and the bond dissociation is easier. By giving smaller energy, you can break it. So, because of this ring, this is the typical example of a ring strain. Because of this small ring, there is extra pressure or stress is applied. That stress is what we call ring strain. Easy, right? Now, 4-member ring. Now, 4 position, now it has a little movement it can do. This position can go up, go down, it can move a little. And then here, not fully eclipsed form, but it can move up and down, so there may be a little torsional strain can be applied if they change their structures. So it's moving around a little 4-member ring, but anyway, we have seen total energy stability wise, this is also quite unstable. 3-member ring, 4-member ring, relatively stressed form. 5-member ring. If it is perfectly on the same plane, then the angle should be matching. But each point of carbon, if you look at, they cannot be on the same plane. It's sp2 structure, right? But this guy is sp3. There is no double bond here. That means they prefer to have a 109, but each position, they cannot be on the same plane. So that's why if 4 of them is similar plane, but one of the carbon should be bended either down or up. That's why there is a partial eclipsed form and partial torsional strain there too. That's why 5-member ring is a little less stable than we expected from planar structures. So that means 3, no movement. It's a fixed eclipsed form. 4 is moving a little like this. 5-member ring, now they are moving a little like this, but none of them is a very stable form. That means they are moving always like this. It's less defined forms. Comparing to this, now 6-member ring is quite interesting. And we have seen 6-member ring is almost no strain, no ring strain. Why? That is the key point of this cyclic alkanes deconformation. 6-member ring is the most common we see in nature. And then this is one example, menthol. 담배 피우는 사람? 뭐 이런 물어 만드는 건가? 담배 뭐 멘톨 담배 이런 것도 있잖아. 박하향 나는 거, menthol. Menthol looks like this. Okay, menthol has this kind of a 6-member ring, cyclohexane structure, and then it has a different functional breakdown. Now, by looking at those conformation, now it has this kind of chaired conformation. This chair is the chair in the beach, right? It's not like a chair like this. So this is a head here, and then you have to lie down, head, arm, and legs like this. Okay. So this is like a Western beach the chair. So with this kind of a structure, conformation it has, and then we can draw different ways. If you look at through this is the projection we have learned before. Then you can see, so some of those structures are, if you look at from here, then this position, one ring and then two hydrogen and one carbon here, and then the other backside here, behind there, proton is behind there. So if you look at this structure, this is very similar to staggered conformation of ethane. Isn't it? So very interestingly, by putting this 6-membered ring by this conformation, then each positions, if you look at, all of them looks like this is a staggered conformation. So when we studied the ethane conformation, staggered was the most stable, wasn't it? And the eclipsed form has strains, either torsional strain or static strain. And by forming this kind of chair conformation, 6-membered ring is a mimic the open structure of alkane, and that's why it becomes the almost has the same stability with the open alkane. So chair conformation. So in the beginning you may need to practice a little. It's not very easy. 한번 테스트 해볼까? 누가 나와서 chair conformation 한번 해볼래? 누가 나오고 싶을까? 김민아 나와서 한번 해볼까? 두개 한번 해볼까? 저런 채 한번 보지 말고 크게 뒤에서 다 보고 각자 한번 그려볼래? 이쁜 채를 그릴 수 있는지 저것도 연습이 필요하거든. 답안지 쓸 때 체어 컨포메이션 그리는 것만 봐도 많이 그려봤구나 하는 거 알 수 있어. 이렇게 문체로 그리면 이것이 두께까지. Not bad. 야, 김민이 그리는 거 보니까 쉽지가 않지? 다음 챕터 노트를 김민이가 어떻게 그려올지 궁금하네. 상당히 뚱뚱한 체어지, 그지? 상당히 비난 체어다, 그지? 그렇게 이쁘지 않지? 체어를 잘 그리는 법, 교과서가 쓰겠다는 방법. 패러럴하게 you draw two lines first in parallel, and then draw one head and then one tail. After you draw everything, you should compare that. These two should be parallel. This should be parallel. And this should be parallel. This should be parallel. If you go too close here, this is a little fat. And if it goes too close, then it may be too thin. So you need, this is kind of reasonable the shape. 생각보다 쉽지 않지. And each bond should be same length, right? This bond and this bond should be same length. Correct? Every bond is a carbon-carbon bond, so that should be same length. 조금 고쳐볼까? 조금 고치면 이 반드가 좀 더 길어져야 되니까 조금 더 길어지고, 그리고 가면 조금 더 길어지고, 가면 조금 나아졌나? Then this one and this one should be parallel. This one should be parallel. This one should be parallel. So some of you draw quite nicely. If it's a little difficult for you, then this is also requires the real practice. Okay, drawing good chair conformation make it much easier to put your answers later. So to make it a little more stereo shape, three-dimensional shape, you may need to put maybe a little thicker one here. If not, sometimes it is a little difficult to see which one is closer to you. Maybe for now you may think this one is closer to you, this one is behind, but if you change your eye angle a little, then it looks the opposite too. There is no information about which one is closer to your eyes. Okay? So to notate that, if you draw a little thicker this way, that's a little more the kind way to show this is closer to you, this is your backside. Okay. Again, similar to the previous projection, if you look through this way or look through this way, then you can see this kind of a projection like this. Now here you see 6 carbons, one carbon and the other carbon behind, one carbon, the other carbon behind, 2 carbon here, 2 carbon here, and then one bridge here, this one and this one. So this is showing you 6 carbons. Okay, thicker one is closer to you, and thinner one is behind there. Okay, so this is the 6-membered ring, the conformation. And then if you go a little further, now here, now if you draw this is 6-membered ring, now you have the protons. Protonating here, protonating here. Now this is a cyclohexane structure. And similar structures we find in nature. Typical example is this sugar, glucose. Glucose has 6-membered ring, even though it has oxygen in the middle, and then it has hydroxyl groups like this. Now, if you look at the proton here, this hydrogen and this hydrogen, are they in the same position? Are they in a similar environment? This proton and this proton? If you look at this way, 6-membered ring, and then if you look at those red ones, and then blue ones. Blue ones, if you look at here, blue ones is facing to the outside. Red ones, they are on the same axis like this. If you have a 6-membered ring, then if you put this axis, so let's say this is like Earth, okay? So Earth here, and this is North Pole, this is the Antarctic Pole here, and then this is equator, Johto. Okay? Then 2 proton, one proton is on top here, and then the other protons is facing to the outside. Energetically, which one is more stable, you think? Axial, the red one or the blue one? Which one is has less strain? Not clear? How about this? Now we look at this 6-membered ring from the top. Okay? This is 6-membered ring, and then 3 hydrogen is coming up here, and then the other 3 here goes down. Okay, those are the axial 6 proton, 6 hydrogen, and then these 6 are equatorial. So we call equatorial hydrogen, axial hydrogen. If you look at this structure, which one is more congested, more crowded? More crowded generates steric hindrance, right? Steric strain. It's more open and then not colliding to each other, that has lower energy. Which one is more stable, equatorial or axial? It looks like equatorial is more relaxed, right? Going to the outside. That's why this the chair conformation of the cyclohexane structure, axial, this axial hydrogen compared to equatorial hydrogen, they are more strained, more stressed, and they have collision this one to this one, and this one to this one. This is what we call 1, 2, 3 position, right? 1, 3 diaxial strain. When we saw there was a staggered form and eclipsed form, there's a 1, 2 position, correct? 1, 2 position we have seen torsional strain, and Cauchy form is also static strain, but that's a 1, 2 position. Now, because of this chair conformation, this axial and this axial, they are quite close to each other. But that's a 1, 2, 3 position, and 2 axial. So 1, 3 diaxial strain is kind of the key word in 6-membered ring, because they have more collision to each other. It's almost a eclipsed form. Okay. So this is the key part of 6-membered ring. So most of those 6-membered ring, we say this chair conformation is more stable, but it's also possible to put both sides going up. And this conformation we call boat conformation. Looks like a boat like this. Okay. In boat conformation, this 1, 2, 3, 4 position, 1, 4 position, they come close together. So there is extra strain happens here. Because of this strain, it's not stable, it goes down. One goes down, then it forms one shell conformation this way, right? If this goes down, then shell conformation goes this way. So there's a two competing conformation for the 6-member ring, boat form and shell form. Which one may be more stable? Shell conformation may be a little more stable than both conformations because of this static hindrance here, static strain here. Now, because of this, now there is axial bond and equatorial bond. Then, depending on the structures, then equatorial, if they have a bigger group on equatorial, maybe they don't have much strain. If they have a bigger group on axial, then that strain will be more severe. That's why 1-3 diaxial strain is important. Now here, one shell conformation like this, then if this goes down, then it may form intermediate boat conformation, right? Going down like this, boat conformation. And if this goes up, then it is another shell conformation, but up and down is a change. How do you know? If you change it like this, now this red color originally was axial. Is changing the conformation, it becomes equatorial now. If you have H and D deuterium, then you can note that those two structures are not same. This is also case of conformation algebra. Like rotation, we have seen eclipse and stability form. In this case, ring flip, shell conformation like this, moved like this. Total form, if all component is the same, then these two is almost equivalent. You cannot distinguish. But if you have a small changes for them, now you can see big difference. This equatorial becomes the axial here. This is what we call ring flip. Flip means changing inside out, it's a flip. This side becomes this side. This kind of a ring flip is happening in 6-member. Okay? Just one more page. If you have choices, if everything is equivalent, 6 position is all hydrogen, then ring flipped 2 structures identical. But let's say if you have 1 bromo cyclohexane, no, you should not put 1, right? Just a bromo cyclohexane. If it's a bromo cyclohexane, then one position, the ring structure, it has axial. The other one, it becomes equatorial. Which one may be more stable? Equatorial, right? Bromine is much bigger than hydrogen. That's why if it comes here, then it will collide with this hydrogen and this hydrogen. Then this one is energetically more unstable. This is similar to eclipsed form of alkane. If this goes down, then this one does not interact with the other side. So this is more similar to stable form. Then if you have an option, then ring flip wise, now you see this is a longer and this is a shorter. Right? So this is more stable and this is less stable. Okay? That's why the population wise, this one has more population than this one. Okay, so today up to here, so we learned about this 6-member ring, the conformational the study, and also naming for those cyclic the alkane. So even though the 숙제 내야 되는 건 다음 주지만 미리 연습 좀 하고 모레 다시 이 부분 가지고 좀 더 다룰 테니까 이 부분은 공부 좀 하고 있는 도움이 될게요. 오케이, 질문 있으면 질문. Any question?